Hello, and welcome to Business Calculus second graphing exercise. In this video, we're going to be performing a process very similar to the previous video. We're going to be doing a long example and applying the entire graphing strategy. So make sure that you take good notes and pause the video at any time if you need to catch up. There's a lot to write down. The example that we would like to graph is the function g of x equals 4x plus 3 divided by x squared. We'll start by determining the domain of this function, and we see that the denominator is equal to 0 when x is equal to 0, so that tells us that the domain is all real numbers except for 0. Next up, we would like to determine the x-intercepts of the graph, and we do that by setting the numerator equal to 0, and by solving this equation, we see that x equals negative 3/4. This tells us that the ordered pair negative 3/4, 0, is the x-intercept of our graph. It's the only one because there are no other values of x that make the numerator equal to 0. We're not going to have any y-intercepts because it's not possible to plug 0 into our function because 0 is not in the domain. For our asymptotes, we're going to look at the limits as we approach 0 from either side. So we'll look at the left-handed limit as we approach 0 of our function. And if we do this, we see that plugging 0 into the numerator isn't going to do anything important. It's just going to make it equal to 3. So we're concerned with the behavior of our denominator. Now, if we plug in a number that is slightly smaller than 0, which makes this a negative number squared is positive. So that means the entire quantity is positive, and we get that the limit is equal to infinity. We get a similar effect if we take the limit as we approach 0 from the right. And since everything is positive, this limit is going to be infinity as well. For the end behavior of our function, we take the limit as we approach positive and negative infinity. As we go towards negative infinity, because the power of the denominator is greater, we see that it dominates the behavior in the cases of very large numbers, and we get that the limit is equal to 0. If we approach positive infinity, we see that something very similar occurs. Since the degree of the denominator is greater, it dominates the behavior. So, for our vertical asymptote for our graph, we have the line x equals 0, and for the horizontal asymptote of our graph, we have the line y equals 0. All right, now let's look at the behavior of the first derivative. In order to analyze the first derivative, we're going to need to calculate it, and it's going to be calculated using a quotient rule of our function. So we take the derivative of the first function times the second function left alone minus the derivative of the second function times the first function left alone, all over the denominator squared. So x squared becomes x to the 4th power. The derivative of 4x plus 3 is 4. If we multiply that times x squared, we have the derivative of x squared, which is 2x, and then we multiply that times 4x plus 3, all over x to the 4th power. A little bit more room to perform our simplifications here. If we distribute the negative 2x to the term on the right here, we're going to get negative 8x squared minus 6x. So that's going to leave us with negative 4x squared minus 6x all over x to the 4th power which after simplification leaves us with this. All right. Now we want to calculate our partition points, and we see that the denominator is equal to 0 when x is equal to 0, and our numerator is going to be equal to 0 when this factor is equal to 0. So this gives us that we want x equals negative 3/2. Using these partition points, we can make our sign chart for g prime. We graph negative 3/2 and 0, and then we're concerned with plugging in values into g prime to figure out in which reasons the first derivative is positive or negative. So let's do g prime of negative 2. And looking at what's going on for our formula, we have negative 2 times the quantity 2 times 2 plus 3 all over negative 2 cubed. We have a negative term, another negative term because it's negative 4 plus 3, and then 3 negative terms in the denominator, so that means that the entire product is less than 0. We need to plug in a number between negative 3/2 and 0, so let's choose negative 1. We play the same game by plugging that value into our original function, so we get negative 2 times the quantity 2 times negative 1 plus 3, and then all over negative 1 cubed. This time, the term with the brackets is going to be positive, so we're going to have 4 negative signs, which means that this entire product is going to be a positive number. And then lastly, we're going to plug in a number that is bigger than 0, so we'll choose 1. And by quickly jotting this down, we see that this is going to be negative again, because we have negative 2, the term with the brackets is positive, and then the term in the denominator is positive well, so we have 1 overall minus sign. All right, collecting this information, the function is going to be increasing in the region from negative 3/2 to 0, and decreasing otherwise. So from negative infinity to negative 3/2, and from 0 to positive infinity. All right, we observe that there are a couple of sign changes in the first derivative. They happen about negative 3/2 and 0, but negative 3/2 is the only point that we're concerned about because 0 is not in the domain of our function g. So we plug negative 3/2 into our original function g to determine the order pair where the local minimum occurs. So we have 4 times negative 3/2 plus 3 all over negative 3/2 quantity squared. This gives us negative 6 plus 3 divided by 9/4. And then after simplification, we get negative 4/3 as our answer. So our local minimum is going to be negative 3/2, negative 4/3. And there are no local maxima as 0 is not in the domain, so its candidacy is revoked. Next up, we're going to talk about the second derivative. All right. In order to analyze g double prime, we're going to need to calculate it. And again, it's going to be another quotient rule. So we take the derivative of the numerator times the denominator left alone minus the derivative of the denominator times the numerator left alone. All over the denominator squared. So we have x to the 6th down there. All right. So taking our derivatives, the derivative of negative 2 times the quantity 2x plus 3 is actually just negative 4, because the constant in front doesn't affect the value of the derivative, and the derivative of 2x plus 3 is just 2. So this gives us negative 4x cubed. And then we subtract from that 2x, which is the derivative of x, and we subtract from that 3x squared, which is the derivative of x cubed, times the quantity negative 2 times 2x plus 3. Again, all of this over x to the 6th power. Doing a little bit of arithmetic, we get negative 4x cubed plus 12x cubed plus 18x squared, all over x to the 6th power. So, collecting like terms and canceling our extra factors of x, we're going to end up with 8x plus 18 all over x to the 4th power. For our partition points, we're going to get x equals 0 like we had before. And we also need to figure out when the numerator is equal to 0. And a little bit of simple algebra tells us that this happens when x is equal to negative 9/4. So we construct our sign chart for g double prime, plugging in our values, negative 9/4 and 0. And then we need to choose points in each of our regions to figure out if the function is positive or negative. So we can choose negative 3 to evaluate g prime at. And then we're just worried about whether or not the function is positive or negative. The denominator for all of these values are going to be positive because of the even power on x. So we're really just worried about the numerator. And if I plug negative 3, we see that we're going to have negative 3 times 8, which is negative 24, which is overall negative. So that tells us that the function is going to be negative in this region. Next up, we plug in a value between negative 9/4 and 0. We'll choose negative 1. And we see that we're going to have a positive number divided by a positive number, so the second derivative is positive in that region. And then lastly, we choose a number that's bigger than 0. We'll pick 1 because it's easy. And by doing the arithmetic, we see that the function is also positive in that region. So our function g is going to be concave up from negative 9/4 to 0, union 0 to infinity, skipping 0 because it's not in the domain of our function. And it's concave down from negative infinity to negative 9/4. Since we do have a concavity change in our domain, that means that we have an inflection point, and we want to evaluate the original function at 9/4 to be able to determine where that occurs. So we plug 4 back into our original function g, and a little bit of arithmetic tells us that this is going to be 32/27. Okay, now it's time to put it all together. Now that we have all of our information, we're going to graph our function g. Let's start by adding in our asymptotes, which we know occur at y equals 0 and x equals 0. Next up, we'll graph our x-intercept, which happens at negative 3/4. So it goes about there. And we have a local minimum at negative 3/2, negative 4/3. So it's going to be down around here. And then we have an inflection point that happens at negative 9/4, negative 32/27. So approximately here. All right. Now, if we were to draw the sketch of our graph, we know that the function is concave down up until our inflection point. It becomes concave up and then begins increasing, of course, at our local minimum. So it's going to have a shape that does something like this. Then approach our asymptote. What we don't know is what happens on the right-hand side of our vertical asymptote. So we're going to need to add some extra values. Okay? What I'm going to do here is to generate some extra points so that we have the information that we need to fill out the right-hand side of the graph and skip ahead a little bit. Okay? Now, with these three values, which you can check their calculations on your own, we're going to add these to the graph so we have some extra information. So we get a point here for 211/4, a point here for 3/5, and a point here for 19/16. And then with this information, we can sort of get a little bit of an idea how the curve is developing in our region. Okay? So what we want to do now is add a computer-generated graph of the same function and compare. All right? With this on screen, we see that we did an okay job. The main mistake that we made was on the right-hand side of the graph. As we approach negative infinity, we made it approach our asymptote too quickly. But otherwise, the curve has the same general shape and information that we see in the one that we drew. All right, now it's time for our question. What was the local minimum of the graph from our example? Was it negative 3/4, 0, negative 3/2, negative 3/4, 3/5, or none of these? Thank you very much for listening.